Assalamu alaikum students. Today we shall continue from the last lecture. We had completed up to the Vesper theory, in which we discussed the different shapes of the molecules by considering the repulsions between the electronic pairs around the central element in the molecule. Because these are the repulsions which will dictate how much angle will be there between the three atoms within the molecule. And we were come across different shapes of the molecules, and we did study how their shapes were named after and how there were different angles mentioned. Now the next topic is that it is somewhat the subtopic of the same Vesper theory, only that we have only selective molecules mentioned over here. These molecules are those which will be present in, we could say, they are present in one plane, in one dimension. That means if you look at this linear structure, these three atoms, they are present in one plane. If this screen is considered to be a single plane, then these three atoms are present in the single plane. It is something like this. They are present on the plane. And if we try to rotate it somewhat like this, they will still be present along one plane. And you can have any direction of this molecule of linear shape to be consisting of atoms on one plane. So this linear is considered to be a planar molecule. We call such molecules as planar molecules. And then this, we have another type of the molecules. Now, although it's again of three atoms, but this one is a non-linear. The angle mentioned is 10.5 degree, and if you remember, this is an example of the water, in which this pink atom is representing the oxygen and the yellow atoms are representing the hydrogen atom. So in this manner, we can have this non-linear structure. It is also called as bent structure, and the angle mentioned is 104.5 degree. Now again, you can see that these atoms, they are all present in one plane. They are present, if you consider this screen as a plane, then these three atoms are present on a single plane. And then moving ahead, this is an example of, if you remember, BF3 molecule. In this BF3 molecule, these are considered fluorine atoms. And inside of it, we have the boron atom. So the angle between the three atoms is 120 degrees. Now again, these atoms are present on a single plane. For this purpose, I can show you by combining three atoms. Now let's suppose if I take this one as one bond, this one is the another bond, and then this is a third bond. They all connected like this. They are all connected through the central atom, and these three bonds are present in a single plane. We can consider one atom is present on this corner, one atom is present on this corner, and another atom is present on this corner. So this is a shape of the trigonal planar, and it is more like a fan shape. So if you try to rotate in any way, these all atoms are present in a single plane. I can bisect all the atoms by passing through a single plane. So this is how we have different directions, but they are all present in the single plane. And the last molecule, this one, the name is already suggested here, square planar. The examples of such molecule are although not present in the AS, but however, we have to understand the shape of such molecule. It is having central atom bonded with the four atoms, but all of them are present in a single plane. Now, how is that possible? I can say this is one atom, this is another atom bonded through the central element, and then another atom is bonding in this direction, and one more atom is present in this manner. So these four atoms, they are these four atoms or these four molecules, we could say, these are all present. These are all present in the same plane. This is how we know about the square planar. So you can rotate in any direction and they will still be present in the single plane. So this is how we have the square planar shape of the molecule. So these were the four examples of the planar molecules, and the rest of the others are they are non-planar. Now, what do we mean by non-planar here? By non-planar, it would mean that if we take the example of the ammonia, let's suppose, in case of the ammonia, the atoms were bonded in this manner. They were present in this manner. Now you can see I cannot pass a single plane which can bisect all the three bonds at the same time. Because if I say the one bond is going away from you, away from me, one bond is going away from me, one bond is coming towards me, and there is one bond which is moving in this direction, which is into the plane. So I cannot pass a single plane which can pass through the three atoms. So this type of the molecule is said to be non-planar. And tetrahedral, which you learned, that is also a non-planar because in that case the fourth bond was present in this direction. So you can see that there is no way by which a single plane can pass through the four bonds or four atoms at the same time. This is the direction of the this is the shape of the tetrahedral. So like this way, we can expect they are non-planar molecule, which includes the tetrahedral. We can also have the trigonal bipyramidal, and also octahedral. They are all non-planar molecules. Moving ahead, our next topic is about the intermolecular forces. Now, in this topic, we will go through some of the examples of the molecules. We will go through the example of the forces which are present between the molecules. The word intermolecular is already introduced in the O levels where where you said that it's a type of the bond or a type of the force which is present between the molecules. So let's suppose if we have an AB molecule which is bonded through a single covalent bond, then this AB molecule will be bonded with another AB molecule like this. This type of the dotted bond will represent the intermolecular force. This is intermolecular force. In the short form, I can write IMF. We will see how these forces are developed and what are the basic reason for these intermolecular forces. So we will see the reasons of these molecule forces. The names are already mentioned here. We have the instantaneous dipole induced dipole forces. In short form, it is called IDID forces. These are also called as London dispersion forces or TDID forces. And then secondly, we have the permanent dipole forces or dipole forces. And thirdly, it is a hydrogen bonding HB. It is a special type or the stronger type of the permanent dipole forces. So we will go through these examples separately to see how these forces exist. To understand this topic, we must go through the topic of the electronegativity, because without electronegativity, you cannot understand which type of the intermolecular force will exist between which type of the molecule. The electronegativity was already introduced at the start of this chapter, which we called as it is a power. It is the power of an element to attract the bonding pair of electrons in the covalent bond towards itself. So when one element will attract the electrons towards itself in the covalent bond, it will be called as the electronegativity of the element. The electronegativity is basically calculated in a special scale which is called Pauling scale. According to that, the value for the fluorine has been given as the maximum value as 4.0, and all the other elements will have values below this. They all will have values lower than this 4.0. The order of the electronegative values in the periodic table is that while moving from left to right across the period, the electronegativity value increases, and when you move down the group in the periodic table, then the electronegativity decreases. This is the order. Moving across the period will increase the value, moving downward will decrease the value. So for this reason, any two atoms of the same element will have exactly same value. So let's suppose if we have the chlorine bonded with the other chlorine, then the electronegative value will be the same for both atoms. If you look at the data section, in there is a table of the electronegative values, according to which the chlorine value is 3.0, and since this is a molecule of two chlorine atoms, the value will be 3.0 each. So we can say the electron density of this whole Cl2 molecule will be symmetrical. This structure is the structure of the electronic cloud. Now you can see there is symmetry on both sides, which means electrons are not being pulled to one side more as compared to the other side. You cannot say there is unsymmetrical distribution of the electron within this Cl2 molecule. The word polarity, which we know, has come from the same concept of electronegativity, which says that those elements, we could say such compounds in which the two elements have different values, they will have two different poles, which are called partial positive and partial negative. If the electronegative difference between the two atoms is significant, then the element carrying the higher electronegative value will attract the bonding pair of electron more strongly, and in this way we could say electron density is now asymmetric. By the word asymmetric means unequal electronic distribution. So which means one side of the compound will be carrying partial negative charge, and the other side of the atom will carry partial positive charge. These are basically said as incomplete charges. We call them incomplete charges. They are not complete charges. Unlike ions, we know ions are of two types, we have the positive ion and then we have the negative ions. They are complete positive and negative charges. On the other hand, these are not the complete charges. We call them partial positive, or you could also say the word partly. You can also say sigma. You could also say slightly. So slightly positive, sigma positive, partially positive, partly positive. These are all the names given to this symbol along with the charge. Now, whenever we have such a case in which the two elements have some significant differences, basically it is said that the difference of two atoms up to 1.9, 0 to 0.4 to 1.9 is said to be a polar molecule. For example, if we take this example of HCl, hydrogen has the value of 2.1 and the chlorine has a value of 3.0. So the difference between the two will be of 0.9. Now this 0.9 value lies within the range of the 0.4 up to 1.9. So according to this, this molecule will be said to be a polar molecule. Why it would be a polar? Because we can see two poles, the partial positive pole over here and partial negative pole. Now what does it indicate? There will be more electron density on one side of the molecule, which will be called as sigma positive side, sigma negative side, and the other end, which carries less electron density, will be called as the sigma positive side. So in this way, we have the polarity in this molecule. Similarly, you can also expect the polarities in the HF, like this one. HCl is already discussed, and then this ammonia, they all have the polarities. The value for the fluorine is up to 4.0. The value of nitrogen is 3.0, just like oxygen. Just like chlorine. Whenever we have the polarity in the molecule, we have to indicate the direction of the dipole. Dipole means having two poles. There will be a dipole within a polar molecule. In polar molecule, the dipole in a polar molecule is what? We have the partial positive and a partial negative sides. Basically, these arrows are indicated. The arrows are indicated in such a manner that the tail of the arrow start from the partial positive side, and the head of the arrow ends at partial negative side. This is the direction of the arrow, and this is a special type of the arrow. You can see that in this arrow you have a cut sign on the tail side. It's not like a pure arrow, it's something different. It has a cut on one side, because these are some specialized symbols for different terms which we use in chemistry. Now here, this dipole arrow is used to indicate the direction of the charges from partial positive side to partial negative side. And you can see here, this is an example of HCl. Now chlorine has a higher electronegative value of 3.0 and hydrogen has a value of 2.1. So partial positive charge is accumulated over the hydrogen atom and partial negative charge is accumulated over the chlorine atom, and then this direction of the arrow indicates the direction of the polarity. Now we will also go through some of the examples in which we will see how the polarity of the overall molecule is measured or it's identified. Overall molecule means whether you should know water is a polar molecule or not, the carbon dioxide is a polar molecule or not, BF3 is a polar molecule or not. How would you know that? we need to identify two things in such molecules. One of them is the bond angle, and the other one is the bond polarity. So we will see at 2 points. Number one is the polarity of the bond, and the second one is the angle of the bond. Angle of the bonds, or we could say the symmetry of the molecules. This is the second thing. Symmetry of the molecules. Now, for this case, we will take an example of the CO2 molecule, carbon dioxide. Carbon dioxide, if you remember from your O-level knowledge, the structure of carbon dioxide was something like this: oxygen double bonded with the carbon, and carbon further double bonded with the oxygen. You remember this structure from your O-level knowledge. Now we will have to see whether this carbon dioxide is a polar or non-polar. If you look at the values of the electronegativity in the data section, you could remember that carbon's value was carbon value is 2.5. This is the electronegativity value of the carbon. And that of the oxygen value is 3.5. So 2.5 and 3.5, if you take the difference of these two, so the difference of electronegativity will come out to be 1.0. That is 3.5 minus 2.5. This 1.0 is in the range of 0.4 to 1.9 for the polar molecules, or you could say for the polar bond. I will say this is the range for the polar bond. That means carbon to oxygen double covalent bond is said to be a polar bond, and we have to decide which element will carry the partial positive side and which will carry the partial negative side. So carbon will carry the partial positive side and oxygen will carry the partial negative side. So I can place the similar partial and negative positive charges over here. So this will become partial positive charge and this will become partial negative charge. And if this is partial negative, then this oxygen will also be a partial negative atom. Now we have decided the polarities of the atoms in the molecule. Now we have to decide the direction of the dipole. As we said that direction of the dipole is from the positive side towards the negative side. That this is the direction of the dipole arrow. So I will show the dipole arrow is from the positive side towards the negative side. And in similar way, you have to indicate the arrow from the carbon towards the oxygen like this. So in this way, we now have the arrows indicating in the opposite directions. If you remember from your physics point of view, these are arrows, and we usually have a topic called resultant vector and vector addition. You find the resultant vector in the vectors addition. Now, how do we have vectors addition for the arrows? It follows the head to tail rule. Head to tail rule, which means if you want to find the resultant vector of these two arrows, you will place the tail of the second arrow on the head of the first arrow. If this is the first arrow, this is the second arrow, then this second arrow will come on the head of the first arrow. And then you'll find the resultant vector by connecting the tail of the first arrow with the head of the last arrow. If you try to sum these two arrows like this, you will see that they will merge on a single point at the center, which means there is no particular direction of the arrow. And as a result of this, we can say the resultant value is 0 or the dipole is 0. So being in opposite direction, these two arrows are in the exactly opposite directions with equal magnitude. By equal magnitude, that is 1.0. This is the magnitude of one bond on the basis of the difference in the electronegative values. And similarly, 1.0 magnitude of this dipole. So 1.0 on this direction, 1.0 on this direction, so they will cancel out each other. And as a result of this, the carbon dioxide is said to be a non-polar molecule. CO2 is a non-polar molecule. It does not contain dipoles in the molecule. Although we saw there was a dipole in the bond in one side, and there was also a dipole in the other side, but those two dipoles canceled out each other completely because of having exactly linear shape. So this is what we have here. The carbon dioxide has equals dipoles and they cancel out, and that's why it is 0. But what if we take an example of the HCN molecule? In HCN molecule, we have three different elements: hydrogen, carbon, and nitrogen. Now in this case, if we consider the dipoles, the hydrogen has the least electronegative value being 2.1. The carbon's electronegative value is 2.5, and the nitrogen's electronegative value is 3.0. You can see that this is the least electronegative, which means the direction will be from the positive towards the negative side. So this is the direction of the dipole from positive to negative side. As compared to carbon, as compared to hydrogen, carbon is more electronegative. So the arrow should move in this direction. And when you compare nitrogen to carbon, it is more electronegative. So another arrow will go in this direction. So both the arrows are pointing in the same direction. As a result of this, if you find the resultant vector of these two arrows, it should be again same rule. The tail of the second arrow must come on the head of the first arrow. And this is what we see here. Tail of the second arrow connects with the head of the first arrow. And then you connect, to find resultant vector, you connect the tail of the first arrow with the head of the last arrow. So it goes in one direction, which means this HCN molecule is considered to be a polar molecule. There is a complete direction in a single, although the molecule was linear. HCN is a linear molecule, but the thing is that their dipoles are not cancelled because of the opposite direction. There are no opposite direction in this case. There is a complete one direction. That's why it does not cancel out, and it's a polar molecule. I can also make some change in this CO2 molecule by doing some assumptions. The assumption is that, or it's considered to be the actual example. If instead of oxygen on one side, I put this sulfur over here, this molecule does exist. It is called as OCS. Sometimes it is called SCO. This is the name of this molecule. Now, in this case, there will be exactly the same dipoles, carbon being sigma positive, oxygen being sigma negative, and this sulfur will also be sigma negative, because as we said that if we check the electronegative value in the table, its value is greater than the value of the carbon. Now the arrow will be pointed from positive side towards the negative side in this manner, but the thing is that the difference of these two arrows are not same. They are not equal. We have already calculated the difference of 1.0 between carbon and oxygen, but although I do not have the value of sulfur, but we can say it will not be 1.0, it will be something different. It can be less than 1.0. The difference between carbon and sulfur will be let's suppose almost 0.5, I can say that. So that that bond will be polar, but not of equal value. So in this case, if you try to find the overall dipole of this small molecule, or you want try to find the resultant vector, then it will move in the right direction. Why is that for? Is it so? Because the arrow on the right side is of longer magnitude, and the arrow on the left side is of smaller magnitude. So when you try to add them together, there will be an overall value or overall arrow or overall dipole on the rightward direction because of the higher value of 1.0 as compared to 0.5. So this will be the polar molecule. This will be considered as a polar molecule having two different magnitudes of the dipoles on each side. So this is how we determine the overall polarity of the molecules. So students, that's all for today. We'll continue our lecture from here onwards in our next class. Till then, take care and Allah Hafiz everyone.